So the last section of this unit is on inverse functions and whether or not they are actually a function or not. So creating the inverses of functions and determining if they are functions as well. So recall that a relation is a set of ordered pairs. Such as the set that we have, 1, 5, 2, 6, 3, 7. Okay? The inverse relation is a set of ordered pairs obtained by switching the x and the y coordinates in each of the ordered pairs. So literally, we're going to take this 5 and the 1, and we're going to switch spots. So that becomes 5, 1, 6, 2, and 7, 3. Notice that the domain of relation becomes its range, and the range of the relation becomes the domain. So they switch. And in inverse relations are reflected over the line y equals x. So before I continue with that, remember that in order for it to be a function, the x values cannot repeat. So as we look at the original relation, 1, 2, and 3, we see that the x values don't repeat. So therefore, it is a function to begin with. But is its inverse a function? So we look at the x values, x, x, and x, the 5, 6, and the 7, they don't repeat either, so therefore its inverse is also a function. So both of these are functions. Now, so what it's asking us to do in the example says the ordered pairs of relation are given to you. Find the inverse of relation, plot the two relations, and observe the line of reflection. Now, the line of reflection should be this y equals x line. The y equals x line is a line that has 0 y-intercept and a 1 slope. So that's not the best line, but you get the idea of where it's supposed to be. So the original ordered pairs I'm going to do in blue. So -2, 0, -1, 5, and -3, 4. -3, 1, 2, 3, 4. So those are the original ordered pairs graph. So I'm going to take and do the inverse in green. So it says find the inverse. So that would be 0, -2. I'll plot that. 0, -2. 5, -1. 1, 2, 3, 4, 1, 2, 3, 4, 5, -1. And the last one will be 4, -3. So 1, 2, 3, 4, 1, 2, 3. And so what you should notice is that each ordered pair, when you flip the x and the y, will make a perpendicular. Let me get this right here. Let me get the line correct. It will make a perpendicular segment. I did not dot the way I asked it to do. Okay, let's turn that to red. All right, we'll give this a shot, see if it works this time. Yes. So it's going to be perpendicular over the line of reflection. So it makes right angles right there. So that is the definition of an inverse. Okay, now that we know what an inverse is, we now have to create an inverse from a given function. So given an equation of a function, f of x, we can create its inverse, which is written f negative 1 of x, and that's not really a whole lot of space for me to write that, but I'll do the best I can. F, color, f negative 1 of x. So f negative 1 of x, and that's what we call it. The negative 1 symbol as an exponent is the symbol for an inverse. So this right here is a must. That is a must-have. We're going to take the x and the y, and we're going to switch it. Okay? So what it's saying down here is that we're going to take the f of x that we just started putting in the equation, and we're going to put y in its place. So what we have is we're going to have an x and a y. And we're going to switch them, just like we did the ordered pairs. In an ordered pair, you took the x, you made it the y, you put the y, you made it the x. So we're going to make this become y. So we have the function y equals x plus 4. So down here, it's going to be x equals y plus 4. And so what happened was the x and the y switched places. Everything else stays the same. The next step says solve for y. So the y is right here. We're going to get everything to go away from the y. So this plus 4 we're going to remove. So we'll use SADMAP to just solve the equation for y. So we're going to subtract 4, subtract 4. We have the equation now, x minus 4 equals y. We've solved it for y. We now finish it up by replacing the y with the inverse symbol. So that is x minus 4 equals f negative 1 of x. And that is how we create an inverse. Alright, so let's try to do a couple more inverse examples. So you're switching x and y and solving for y. Okay, so that's the basic direction. Switch x and y, solve for y. Alright, so this becomes x equals negative 1 half y plus 1. So reminder, the x and the y are switching. Alright, and let's just solve for y. So remember that we're going to use SADMAP to solve. So we will subtract first. X minus 1 equals negative half y. We're going to multiply both sides by negative 2 because that's the reciprocal. Please note that I'm using a parentheses to multiply everything on the left-hand side. That's negative 2x plus 2 equals, and then here is where we're finished, so it's f, negative, it's not f, it's g. G, negative 1 of x. Okay? The B example is x equals y squared plus 1. So notice that everything stays exactly where it was except the x and the y. The squared is still there. It's just now on the y. Use SADMET to solve. Subtract 1. Subtract 1. X minus 1 equals y squared. Take the square root. Plus minus square root x minus 1 equals, this is an h function, so h negative 1 of x. Alright, so the last thing we need to do with inverses is verify that they are inverses. Okay, so if two functions are inverses, if and only if both of their compositions are equal to x, just like the little box at the top says, okay, x. Now compositions, let's talk about compositions again. Compositions mean that you're going to take and substitute one into the other. This was a topic that was covered on Friday, the 11th, 9/11. So we're substituting one function into the other. And it doesn't matter which one you do first, you're supposed to do both of them. So determine whether the functions are inverses. And so your answers are either going to be yes or no. Okay, and so the reasoning would be they're not because it didn't equal x at the end. So you're going to take one function and plug it into the other function. So that's going to look like this. 4 thirds, open a box, open a parentheses, plus 8. And then you're supposed to plug in 3/4 x minus 8, which is the top equation that went into the bottom equation. So as we multiply this, it's 4 thirds, okay? So it's 4 times 3, 3 times 4. That's 12 over 12. 12 x over 12 x. It's 4 thirds times negative 8. 4 thirds times negative 8. That's 4 times 8, 32. Divided by 3, so it's minus. Sorry, I need to do that in red. 32 over 3, and then we get the plus 8 that's on the end. So we look at this and we say, okay, can anything cancel out? Yes. The 12s cancel out. And that's x. It's not supposed to be an x on the bottom. It's supposed to be an x. So my apologies for that. No x on the bottom there. And then you take negative 32 over 3, and you add 8 to that. You get negative 8 thirds. And that's all we can do. So that's done. Okay? So we'll say, all right. Are they inverses of one another? If they are inverses, the only thing you will end up with at the end of the problem is an x. And we've got more than just an x there. So these are not inverses. Because when we're done, we're only supposed to have an x. So as we look at the example B, hopefully that's what's going to happen, so that we see an inverse situation. So we'll do the same thing. We'll take the top function and we'll plug it into the bottom function. So this is going inside of this. So 3 square root parentheses minus 3. So we'll put all that in there. 1/9 parentheses x plus 3. And that is squared. Now take this slowly, okay? It's wanting us to square root. Okay, so we're going to square root the things that are on the inside. So when we square root 1/9, you're going to get 1/3. When you square root this parentheses, the square goes away. X plus 3. That leaves us with this 3 in the front, 3, and that's a multiplier, and this 3 in the back. So now we multiply. So we have 3 times 1/3, that's 1. So we have x plus 3 minus 3. Now we subtract. The 3 minus 3 is 0, leaving us only with the x remaining in the problem. This is what happens when you have inverse. Yes, these are inverse.